In part 3 of our introduction to nonparametric statistics, I want to talk a bit about the value of nonparametric statistics. I hope that once you see the value, you'll understand that you are in the right course. This is something that you want to learn. In fact, you might start to wonder, why doesn't everybody know about and use nonparametric statistics? So we'll spend a few minutes talking about that as well. Finally, I'll wrap up by giving you an overview of the major features of this course. Not the specific topics, but what I would like to accomplish in terms of your general learning throughout the course. Let's talk about the value of nonparametric methods. Why use them? First, and probably what comes to people's minds most often when they think about nonparametric statistics, is that you do not have as many conditions for valid inference. You don't have the same strict assumptions that you do for most parametric procedures. Because of that, you can use nonparametric methods with small sample sizes. And in fact, some people mistakenly believe that that is the best place for nonparametric methods with small sample sizes, but as you will see, that's not the case. It's just that you can use nonparametric methods regardless of the sample size. The estimates and inferences that we make should, in my opinion, always be matched to the level of measurement. That is not the case with parametric methods, where we assume that we have at least an interval level of measurement when we use those methods. With nonparametric methods, we can consider the actual level of measurement and then pick the method that is most appropriate with that level of measurement. Anytime we work with data, we are actually working with discrete values. Even when we consider the underlying construct as continuous, the reality is we do not measure that in a continuous form, but rather in a discrete form. Thus, the actual distributions we're working with are discrete distributions, not continuous. When we use parametric methods, we're often using continuous distributions as models for what in reality are discrete distributions. With nonparametric methods, we use the discrete distributions. Thus, we are matching the reality. Every time we use a parametric method, we are actually approximating the error rate. That's probably a new concept to you, but think about it a moment. What do? You set the type 1 error rate at, say, 0.05, and then you use a continuous distribution, such as the normal distribution, and you decide where the critical value is based on that distribution. Well, if you're not really using a continuous distribution, and if the underlying distribution is not really normal but an approximation, then you're in fact calculating an approximate critical value that corresponds to an approximate error rate. But with nonparametric methods, many times we can calculate exact error rates. They are not approximate. They're based upon distributions that we literally do know, and therefore we can calculate what the error rate actually is. This would surprise many people, that nonparametric methods are often more powerful for making inferences than parametric methods. Some people shy away from nonparametric methods because they've heard that parametric methods are most powerful. That is only true if all the conditions for the parametric methods have been met. Otherwise, a nonparametric method may well be more powerful. So with the actual distributions we work with in behavioral, social, and medical research, the most powerful inference will often come from using a nonparametric method. And then the inferences we make can be adapted to directly answer the questions of interest. When we deal with parametric methods, we are stuck with certain hypotheses, like, is the mean for the treatment group greater than the mean for the control group? That may in fact be what we're interested in, but maybe not. Maybe we're interested in the proportion of individuals who were helped by the treatment, or whether most individuals were helped by the treatment. We can decide what our research question is and then create statistical hypotheses that match that research question, and from that, use a method of inference that is consistent with that statistical hypothesis. We are not bound to particular hypotheses because they happen to be related to distributions that underlie our data or are perceived as underlying our data. This, to me, is one of the most important reasons to consider nonparametric methods, that we can actually address the research questions that are of interest. Many of the nonparametric methods can be explained within a common framework. That is, there's a beautiful consistency that we can build that links these all together. Very much like you have general linear models that link together many parametric methods, we have different ways of linking together in a common framework nonparametric methods, but furthermore, we'll take it a step further. We can actually explain many parametric and nonparametric methods together within a common framework. That extends the frameworks that you've learned with parametric methods to become an even broader, beautiful network of methods. And then nonparametric methods can be less difficult to understand. If the method is less difficult to understand, perhaps we can more fully understand it. Perhaps it's an easier route to learning more deeply about the methods that we use. I have often considered that nonparametric methods lead to much more intuitive understanding of statistical inference concepts, and so, in fact, I will be taking advantage of that to review statistical inference concepts, and I believe that you may come away with a deeper understanding of those than you have in the past. That is all because these nonparametric methods are straightforward and less difficult to understand. Now, as you look at all these values to nonparametric methods, I hope you're asking yourself, why not? Indeed, why not? Let's talk about the characteristics that impede progress with using nonparametric methods. I'll put these into two categories: myths and difficulties. The first myth is that nonparametric methods are not as powerful as parametric methods. That's the overwhelming myth, and as I've already described, that comes from a reality. That is, if you have exactly met the conditions for valid inference of the parametric method, it is going to be more powerful. But it is a mismatch for the practical nature of our data in which those conditions are never exactly met. One myth about nonparametric methods is that you cannot make inferences with these methods because they focus on the sample rather than the population. But as you will see throughout this course, we will frequently make inferences. Indeed, we will make inferences for every method that we consider. Another myth is that the methods are not for use with quantitative data, only categorical. Well, indeed, methods that are for categorical data are nonparametric, but these do extend to quantitative data as well. I can logically convince you of that right now. Any quantitative data can be made categorical. Therefore, any quantitative data could be analyzed with nonparametric methods. But beyond that, we can actually take the quantitative data without changing it and use nonparametric methods. We'll do that. Some people believe that because of the different kinds of hypotheses that we often use for inference with nonparametric methods, that these hypotheses don't really match what they are used to seeing and therefore are vague or uninteresting, when in fact I believe the hypotheses often are more related to the researcher's hypothesis than many of the hypotheses that are more traditional. So far from considering these hypotheses as vague or uninteresting, I would say these hypotheses are often more interesting. And then for those who think that, yes, you can make inferences with nonparametric methods, some of these people think, but you cannot construct confidence intervals. You'll quickly learn, because you'll be doing it, that in fact this is a myth. You can construct confidence intervals. As with any statistical method, there are difficulties. Perhaps the main difficulty in using nonparametric methods are they're not as well known. So what does that mean? If you use nonparametric methods in a research study, then when you write up those methods, you need to go a bit further than simply saying, here is the particular inferential method that I used, and instead, you have to actually explain a little bit about why you use that method, and perhaps even teach the reviewers of the manuscript a bit about the method. One of the things I'm going to do is talk about that throughout the course. That is, I will not assume that the people who read your work know about nonparametric methods, so we'll talk about how we can get these manuscripts accepted when we use nonparametric methods by giving convincing arguments right within our manuscript. In time, I hope, if enough people do this, these methods will become more well known so that we don't have to argue for them every time we use them. Once upon a time, these nonparametric methods could not be found in statistical software, but now most of them are. When I say they're not fully implemented in statistical software, what I mean is that not to the same degree as the more well-known parametric methods, but with every year that goes by, we see this becoming less and less of an issue as more and more advanced nonparametric methods make it into the statistical software. Everything we do in this course is going to be done primarily with statistical software. So this really is not the difficulty that it used to be. I do find that because we do not teach anything about nonparametric methods in our introductory courses, I have to start my instruction earlier on than I would like to. I would love to be able to plunge into some of the more complex methods, but in fact, we need to start at the beginning, because what we could be teaching in introductory courses about nonparametric methods are going to have to be included in our nonparametric course, which is why I'm going to take advantage of that and do a better job of teaching statistical inference than I believe I could ever do with parametric methods. And then one final difficulty is that these methods often require high computing power and time. As you can imagine, this is also less of an issue as computers become more powerful. Furthermore, we also have tricks that we now use in order to cut down on computing power and time. So these difficulties here, not as well known, not as fully implemented, not taught in traditional introductory courses, and often requires high computing power and time, these difficulties have less and less of an impact on actual practice. So I believe that nonparametric methods are not only viable, but a preferred method of analysis for many of the research studies that are done in the behavioral, social, and medical sciences. Indeed, in mathematical statistics, the value of nonparametric methods has been known for a long time. The American Statistical Association even has a division for nonparametric statistics, which I happen to be a member of. The point being that in some domains, the value of nonparametric methods has been well known for a long time, and I hope that becomes more and more of the case in my own domain. As we move forward in this course, here are some of the features that I want to embrace. I want to take advantage of new opportunities for learning fundamentals of inference, that is, testing hypotheses, calculating power, constructing confidence intervals, not only new ways of doing these, but also new understandings of what you already do. I am going to focus on developing conceptual understanding of nonparametric methods. What do I mean by that? A lot of times when nonparametric methods are taught, They are presented with so-called calculator formulas. That is, formulas that hide what's going on, but instead make it easy to do a hand calculation. We don't need to do hand calculations. We have the computer. So when I present formulas, they're going to be formulas that help you see how everything works, rather than making it simple to calculate some numbers. We want to know how to conduct inference in all data situations. Some nonparametric methods say you may not have ties in your data. Well, obviously, we will often have 2 or more data points of the same value when we collect our data, so we're going to go beyond this condition and establish methods that are more general, that allow you for correct inference regardless of whether you have ties or other kinds of conditions, sometimes that go hand in hand with nonparametric methods. I want to help you develop a general framework, not only for all the methods we use in this course, but also a general framework that extends to parametric methods. And then another feature of the course is that throughout, I want to consider the research design and the level of measurement. These are not part of statistical analysis, but I want to consider them because they heavily influence statistical analysis. When we address issues that are separate from statistical analysis, we'll better know how to design our studies and what kind of measurement we might need in order to be able to test the hypotheses we're interested in, and then we will use these decisions to inform the statistical analysis that we do and the analytic choices that we make.